I remember trying to run this big analysis once, just a personal project,
Mm.
and my poor laptop basically just ground to a halt. I mean, it felt like it would take days. Now scale that feeling up, way up, to the
Volume.
cosmos. That's pretty much the headache cosmologists are facing right now.
Yeah, exactly. These new surveys, DESI, Euclid, they're amazing, but they're generating just these immense data sets. We're talking petabytes.
Petabytes, wow.
And the tools we use to understand what's going on, like the effective field theory of large-scale structure or EFTOF, LSS, well, they're hitting what you called a computational wall.
Right. Trying to model galaxy clustering with that much data.
Precisely. It demands millions, literally millions, of really complex calculations. And traditionally, running a full, say, Bayesian analysis, that could tie up a supercomputer cluster for days. Makes quick research turns, well, almost impossible.
Okay, so that's where Effort.jl comes in, the effective field theory surrogate.
That's it. The whole idea, the mission, is to break down that wall, take those massive data sets, analyze them properly, but do it fast. We're talking maybe a few hours on just a regular laptop.
Okay, hold on. From days on a supercomputer cluster
Yeah.
to a few hours on a laptop.
Oh.
That's a massive leap. How does Effort.jl actually do that?
It's really a couple of things working together. First, the software itself. Traditional tools, something like PyBird, might take seconds, maybe even minutes, for just one likelihood evaluation.
And you need millions of those.
Exactly. Millions. So the time just explodes. Effort.jl is written in Julia, which is known for performance. But the real key is it uses a neural network surrogate model.
Ah, okay. AI.
Right. This surrogate computes the essential outputs, the galaxy power spectrum multipoles, incredibly fast, like around 15 microseconds on just one CPU core.
15 microseconds. Okay, that's ridiculously fast compared to minutes.
It's a total game changer for speed.
But you mentioned it's not just the neural network speed up. There's something about it being differentiable.
Yeah.
Why is that so important?
Ah, yes. Differentiability. That's the other major unlock here. See, older methods often rely on random walks, like standard MCMC, to explore the parameter space. They sort of stumble around, hoping to find the best fit. It takes forever.
Lots of wasted steps.
A lot of wasted steps. But because Effort.jl is differentiable, we can calculate gradients. It means we know the slope of the likelihood of function.
So you know which way is uphill to the best answer.
Exactly. We can use really powerful gradient-based sampling techniques, things like Hamiltonian Monte Carlo HMC or NoUTs, the no-U-turn sampler, via another Julia package called Turing.jl. Instead of stumbling, you follow the steepest path right to the peak likelihood.
Which means you need far, far fewer steps to get a reliable answer.
Exponentially fewer, yeah. It dramatically reduces the number of evaluations needed to converge.
Okay, so it's this combination of like high-performance language, a super-fast neural network surrogate, and this clever differentiable approach using gradients. Is pretty specialized stuff.
It really is. And building that kind of advanced tech, whether it's AI training or specialized software development, takes real expertise.
Which seems like a good moment to mention our sponsor.
Absolutely. This deep dive is sponsored by Embrasilk. If your business is looking into AI training, automation, maybe custom software development, or even just trying to figure out where AI agents could really make a difference for you.
Or maybe integrating complex systems like these.
Right. You should definitely check out embersilk.com. They handle all sorts of AI needs.
Good to know. Okay, back to Effort.jl. Speed is one thing, but accuracy is everything in science, right?
Yeah.
When you swap out established physics calculations with a neural network, how do you ensure you still trust the results? How is it validated?
That was absolutely critical. You can't just be fast, you have to be right. So Effort.jl was put through its paces, tested against very high-precision simulations, the PT challenge ones, and also against real observations from the BIAS-F survey, a big, well-understood data set.
And the results?
Excellent agreement. The outputs match the traditional trusted pipelines, like PyBird, very closely. Any small differences were well within what we'd expect from just random statistical fluctuations, Monte Carlo noise, we call it.
Okay, so it's accurate. And what was the practical upshot of that validation?
The big one was convergence time. Using Effort.jl, a full analysis converged in about 10 minutes. On a laptop.
10 minutes compared to hours or days on a cluster.
Exactly. That difference isn't just incremental. It fundamentally changes how researchers can work. You can iterate, test hypotheses much faster.
You also mentioned it's not a black box AI. There's this physics-based preprocessing. What does that mean?
Right. Transparency is key for adoption. They didn't just train a network on raw inputs and outputs. They used known physics to guide the AI.
How so?
Well, they scale and normalize the network's outputs using things we understand well from physics. For instance, they use the scale-independent growth factor, DS. That's a standard cosmology concept describing how structure grows over cosmic time. It helps keep the network grounded in physical reality.
So physics informs the AI structure.
Exactly. And they even used other clever tricks like calculating that growth factor, DZ, used to involve solving an ODE, a differential equation. Took about 150 microseconds. Not huge, but, a small bottleneck.
Okay.
They used something called symbolic regression to find a simple algebraic formula that does the same job. The result, that calculation went from 150 microseconds down to just 200 nanoseconds.
Nanoseconds, wow. Shaving off every bit of time.
Every little bit helps when you're doing millions of evaluations.
So pulling this all together, Effort.jl seems like this really robust, fast, and trustworthy toolkit. Perfectly timed for these huge new datasets coming from DSI and Euclid.
I think so, yeah. It's poised to make a big difference in analyzing that next generation data. But, thinking bigger picture for a second.
Go on.
The whole approach, this idea of building a fast, differentiable emulator that's still informed by physics, it's quite modular. You could potentially apply this kind of framework to other really complex systems.
Like what?
Well, think about things like weather forecasting or climate modeling, highly complex, nonlinear systems, or maybe even simulating new quantum materials. The potential's there for this type of tool to be useful well beyond just cosmology.
A really interesting thought, this technique, potentially speeding up discovery across different fields. Fascinating stuff. Well, that's all we have time for on this deep dive. If you enjoyed it, please do subscribe to the show. And hey, if you have a moment, maybe leave us a 5-star review. It really does help other curious minds find us. Thanks so much for tuning in.